Hey guys, Mr. O'Sullivan here. Hey, we're going to go over AB practice exam number one, which was the homework that was due this morning. And this is again going to be a great kind of walkthrough. Hopefully, this is going to be similar to the format of the actual exam. It's also going to be format of the unit test that you guys are going to have tomorrow. So hopefully, if you're good on kind of this format, these types of problems, you'll be all set. All right. Before we dive into it, again, I'd like to thank Michelle Crummell, AP IB teacher in North Carolina at Myers Park High School, and she was the one that developed this problem. And this is it's an awesome problem, and it is not easy to write an airtight AP free response problem. So kudos to her and a great job. Okay, so let's dive in. So, and again, if we go to problem number one, and you'll notice, again, we're going to have two free response questions. First problem is going to be kind of a FRQ on steroids. And if you notice, it's 25 minutes in length. And problem two, just a quick looky-loo. Problem two, part B, is going to be kind of the normal FRQ that we're expecting, about 15 minutes in length. That's kind of what we practice all year. So, again, the first one's going to be a little bit longer, probably 4 or 5, maybe 6 sections to it. The second one, a regular FRQ that we're expecting, is probably going to have like 3 or 4 parts to it. Okay, so question one. We're given a data table that has first row is days, time in days, and then the second row is H and T, which represents, looks like the number of butterflies for a particular day. Okay, so the number of butterflies spotted in Amelie's garden after or each afternoon is modeled by a differentiable and increasing function. Okay, so I know my function H is differentiable and increasing on that interval from 0 to 14, where T is measured in days. Selected values of H and T are given in the table above. Okay, so that's all good. So part A says use the data in the table to find an approximation for H prime at 8. Using correct units, interpret the meaning of this value in the context of the problem. Okay, so I'm just going to pull this one down here. And so if I'm looking for an approximation of H prime at 8, and then I want to use correct units, I also want to interpret what that means. So in my table, I'm really looking at T of 8 would be located right between the 7 and the 9 in that row. And so what I'm going to use would be this coordinate pair and this coordinate pair on either side of where the 8 would be. So I'm going to have H at 9 minus H at 7 over 9 minus 7. So my approximation, H prime at 8, is approximated by H at 9 minus H at 7 over 9 minus 7. Can't stop there because that's still just, I got to get rid of that function notation. So H at 9 is 11 and H at 7 is 7. So I have 11 minus 7 over 9 minus 7. I can stop there. That's a numeric answer. And my units, units from that row that gives me my H values are number of butterflies, and then T is in days. So that is going to be the number of butterflies per day. Now, the last part of this, the interpretation, I'm going to say that at day 8, the number of butterflies is changing I use changing, I don't even have to care. I can look at that, this expression and see pretty quickly that it's positive, but I can go with changing because that would cover increasing or decreasing. I don't have to commit to one or the other. I could just say is changing at a rate of 11 over 7, 11 minus 7 over 9 minus 7, butterflies per day. And that's my interpretation in the context of the problem. Okay, so that's part A. Okay, part B, explain why there must be at least one time t in the open interval 0 to 14 such that h prime of t is equal to 1.5. Okay, as soon as I see must be at least one time t, I hope that rings a bell in your head, and I hope you're thinking of it's got to be there's one of our theorems is at play here. Well, what would be maybe good candidates for which theorems this might be? Squeeze theorem? Probably not squeeze theorem. Extreme value? Probably not. Maybe IVT? Could be IVT. Maybe mean value theorem for derivatives? That could be in play. Doesn't look like it's necessarily FTC, part 1 or part 2. So I'm probably looking either IVT or MVT. Well, how can I kind of know, maybe differentiate between the two of them? One thing I might look at is that they're giving me in part B here, they're talking about H prime. And the other information I'm given in my table is what? It's H of t. Okay, that should clue me in since they're not the same. Since it's not, H at prime given in part B and H at prime in my table, that should tell me that it's not IVT, okay? Because when I'm given like the function and then the derivative, some value of the derivative, I should be thinking mean value theorem for derivatives, okay? Okay, so let's go with that, and then let's see how we can answer that part B using mean value theorem for derivatives. So if that's the case, I'm going to say, all right, let's copy this. So I'm going to say, well, if I think about MVT for derivatives, might be good. We got to remember that f of x is two things. It's continuous on the closed interval, a to b, and f of x is differentiable on the open interval, a to b. If I've met those two criteria, then my conclusion, this is my if, then my conclusion, then there is at least one x equal to c in my open interval a to b, such that, big finish, such that what? Such that f prime at c is equal to f at b minus f at a over b minus a. Okay, now I'm kind of just throwing that back at you because I think that's a good review of mean value theorem for derivatives. In this problem, if I'm in exam mode and I'm answering this question, I'm basically going to just say, well, this is how I'd answer it. I'd say that because, okay, so again, what I just listed up there, that's kind of my cookie cutter definition of mean value theorem for derivatives. I'm not going to get any points if I just put that. I mean, the reader's going to look at that and say, great, you memorized some definition of mean value theorem for derivatives, but you can't put it in context of this particular problem. So that's what we have to do now. So I'm going to say because h of t is continuous on my interval from 0 to 14 and differentiable on the open interval, same 0 to 14, but this time open. Okay, then I've met my two conditions. Then I can conclude. Then there is at least one. Okay, I'm using not x but t. There is one t equal to, you can call it c if I want, such that h prime at c is equal to, and now what I'm basically doing is replicating the right side of my equation of my conclusion in the context of my problem, which is going to be h at 14 minus h at 0 over 14 minus 0. Got to go one more step. H at 14, go back to my table. H at 14 is 22 minus h at 0 from the table. That's 1 over 14 minus 0. And that's equal to, I'm liking this, 21 over 14, which is equal to what I'm given in the problem, the 1.5. Bada boom, bada boom. Okay, so that is my answer to part B. Okay, so by the mean value theorem for derivatives. Again, once we see this wording, why must there be at least one? Okay, that ought to ring in our heads, because for nearly all of our theorems, our conclusion starts out that way. Then what? Then there is at least one, yada, yada, yada. Okay, awesome. All right, part C. Approximate the value of the definite integral from 0 to 14 h of t dt using a left Riemann sum on the subinterval 0, 5, 5, 9, and 9, 14. Is this approximation greater than or less than the actual definite integral 0 to 14 h of t dt? Give a reason for your answer. Okay. Part C, I'm going to go up above here, and I'm going to do my work for part C right here. So what I'm going to do is I'm going to approximate the definite integral from 0 to 14 h of t dt. Now, since I'm approximating, I'm going to use my approximation symbol, not an equal sign. And I want to use a left Riemann on my interval 0 to 5, 5 to 9, 9 to 14. So they're being specific. Now I want to break that up. So I'm going to go 0 to 5. I'm going to just put a little box. So that's one interval. And then 5 to 9, notice it overlaps. So I'm going 5 to 9 on that one. And then the last one is 9 to 14. Okay, so I kind of got a red, blue, and a green box on my table there that represents the subintervals I'm asked to use. And again, it's a left Riemann sum. So the first thing I want to do in my red interval there, I want to circle I always want to circle the left y value, which in this case is going to be 1. I'm going to do that for my blue box, and then for the green box, which is 11. So I'm going to be using those 1, 4, and 11 are my y values. Okay, now what I want to do is I want to get my delta t. So in my first interval from 0 to 5, that's an increase of 5. 5 to 9, that's an increase of 4. 9 to 14, that's an increase of 5. Okay, now I'm just going to build my left Riemann sum. So it's going to be 5 times that 1 plus 4 times the 4, y value of the second interval, plus 5 times 11, which is 1 more than 10. Okay, that is my left Riemann sum. Now the question is this approximation greater than or less than the actual definite integral? Okay, well, if I think about it, it's a left Riemann sum. What do I have to look at in terms of h of t to determine whether that estimate, left Riemann sum, is going to be less than or greater than that. Well, you're right. It's going to be what's h doing on that interval from 0 to 14. Well, right here, they told me it was increasing. So if that is increasing, I can just sketch this just to remind myself. If it's increasing, again, it doesn't matter if it's increasing concave down, increasing concave up. If I do a left Riemann sum, cap that bad boy right there, that means that this is going to be where my approximation is less than my actual definite integral. So I'm just going to show this. I'm going to impress the readers. I'm going to show that this is less than the actual Riemann sum. H of t dt, and I got to add here because because what? Because h of t is increasing on that interval from 0 to 14. Good. Awesome. All right. Rolling right along. Okay. Part D. Number of bees spotted in Amelie's garden during the same 14-day period. Okay, now, again, we're changing gears. We were talking about butterflies in part A, B, and C. Well, now we're throwing something different at you. It's the number of bees in the garden during that same 14-day period, modeled by the function g of t is equal to that, where t is measured in days. At time t equals 8 is the number of bees increasing at an increasing rate, increasing at a decreasing rate, or neither. Based on your answer, what can you conclude about the graph of g of t at t equals 8? Justify your answer. Okay, this is getting a little salty. So what I want to do, I'm going to copy this down below. Okay, so when we copy that down below, there's part D. Okay, so we're looking, and the trick is going to be, we've got g of t is equal to 7e to the 1/7 times quantity t minus 1 plus cosine of the quantity 2t minus 16 over that interval for closed interval from 0 to 14. Okay, well, they're asking us at t equals 8, is the number of bees increasing at an increasing rate? So that's kind of one option. Is the number of bees increasing at a decreasing rate, or is it neither one of those? And then based on our answer, what can we conclude about the graph of g at t equals 8, and then justify? Well, what we need to do, obviously, is look at, might be obvious, it might not, is look at g prime of t and also g double prime of t. And then take the first derivative, evaluate it at time 8, and then the second derivative at time 8, look at the signs of those derivatives. That's going to tell us whether the number of bees is increasing at an increasing rate or increasing at a decreasing rate, or could be decreasing. And it doesn't matter if it's, how it's decreasing, but if it's decreasing, then that's going to be our neither selection. Okay, so we look at g prime of t. Well, if I'm taking the derivative of this, I'm going to look, well, I know this is going to be, this exponential part is going to be the whole shoot and match just the way it is, as it's an exponential, then times the derivative of the inside function, which is just going to be times 1/7. Okay. And then move on to the second part, plus the derivative of cosine is going to be negative sine. So this is really, I'm going to treat that just like negative sine of 2t minus 16. Then don't forget chain rule times 2. So that's g prime at t. Now again, I'm going to be interested in g prime at 8 in a second. While I've got this right there, I'm going to simplify just a little bit. I wouldn't simplify, but what I've got to do is I've got to find G double prime. So I want to make life a little bit easier. And I'm just going to rewrite G prime of t is equal to, hey, the 7 and the 1/7 cancel out. So this is really just E, the 1/7 times quantity t minus 1, minus, and I'm just going to move this 2 up front, minus 2 sine 2t minus 16. Sweet. Okay, now, second derivative, I'm taking the derivative of that. Golly gee, this is going to be really just this again, e to the 1/7 t minus 1 to the exponent times derivative of the inside function, which is the exponent, 1/7, minus, well, this is just going to be 2, derivative of sine is going to be cosine. We're back to cosine again. So yeah, we're kind of oscillating back and forth. And then times, again, derivative of the inside function times 2. Okay, so now what I can do is I can plug in G prime at 8 is equal to E to the 1/7 8 minus 1 minus 2 sine of 2 times 8 minus 16. I'm looking at that, and if I just continue that, that's going to be e to the 1/7 times 7. That's just going to be e to the first. That's going to be e, and then this is going to be minus 2 times, well, that's going to be sine of 0. Well, sine of 0 is 0, so that's just going to be e. So that's e. And so that is obviously positive. So G prime at 8 is positive, which tells me that G at t is increasing, right? So G at t, I'm just going to write that out here. Therefore, G at t is increasing. Okay, so that means it looks like neither is out of the running because it's increasing. I don't know if it's increasing at an increasing rate or increasing at a decreasing rate. That's what the second derivative is going to tell me. So now I do G double prime at 8. That's equal to E to the 1/7 times 8 minus 1 times 1/7 minus 2 cosine 2 times 8 minus 16 times 2. Okay, if I simplify this first part, well, this is basically kind of what I had above here, and that's going to be 8 minus 1 is 7 to 1/7, so that's going to be 1/7 e. Only difference is I've got this 1/7 kind of coefficient there. Now, minus, let's look at this. That's going to be cosine of 0. Cosine of 0 is 1, so that's going to be minus 4. So I have 1/7 e minus 4. Well, that's going to be a negative number. I mean, e is about 3-ish. So, I mean, I've got really 3/7 minus 4. That's definitely going to be a negative number. Therefore, okay, so really the second derivative is negative. So that means what? That G at t is increasing, but we can kind of go our final conclusion here, and we say that because G prime at 8 is positive and G double prime of 8 is negative, therefore what? G at t is increasing. So it's this one here. It's going to be increasing at a decreasing rate. Is increasing at a decreasing rate. Okay. Now I'm not done. I got this last part here based on your answer. What can you conclude about the graph of G at t equals 8? Well, that means what? If it's increasing at a decreasing rate, it means that the graph looks like that. So my conclusion is going to be, therefore, G at T is concave down at T equals 8. And that answers the second part, the last part of that question. Okay? Sweet. All right, that's a little salty, but I like salty. Okay, the last part of this first question is part E. So we've got, and I don't think we can just copy this down because we don't need anything other than just what's in part E. So I'm going to copy that down. All right. So part E, and I think this is definitely the hardest question anywhere on this this homework set. So it says the number of bees spotted in Amelie's garden can also be modeled by the function b at x equals 50 times the square root of k plus 2x, where x is the daily high temperature in degrees Fahrenheit, k is a positive constant. When the number of bees spotted is 100, the daily high temperature is increasing at a rate of 2 degrees Fahrenheit per day. According to this model, how quickly is the number of bees changing with respect to time when 100 bees are spotted? Okay, this one it's challenging, especially because we're changing gears again. This is another function that's giving us the number of bees, but unlike what we had in part D, it's the number of bees in terms of the daily high temperature, which is x. In part D, we got the number of bees in terms of time in days. Okay, so again, this is different. Slightly, we're still getting the number of bees, but the independent variable is different. Okay. Well, what I would do on this type of problem, any kind of problem, is try to like convert our words into calculus speak, calculus notation. So how about this part? When the number of bees spotted is 100, well, let's say that B is equal to 100. Okay, that's kind of given. How about this part? The daily high temperature is increasing at a rate of 2 degrees Fahrenheit per day. So the daily high temperature is increasing at a rate of 2 degrees Fahrenheit per day. Well, would you believe that is the change in x per the change in time is equal to 2. Okay, that's what that part of that sentence means. The daily high temperature is increasing at a rate of 2 degrees Fahrenheit per day. So dx dt is equal to 2. Okay. According to this model, how quickly is the number of bees changing with respect to time when 100 bees are spotted? Okay. Well, and this is maybe the most important thing we need to translate, is we're saying, what are we asked to find? We're really asked to find how quickly is the number of bees changing with respect to time. Well, number of bees changing with respect to time, I hope you might be able to come up with, is the change in the number of bees with respect to time. And then when 100 bees are spotted, we're basically saying that such that B, the number of bees, is equal to 100. Okay? Well, all right. Well, given, I mean, that's kind of giving us a start maybe. Well, how about this? If we're looking really for dB dt, it would be nice to have an equation for B. Okay, and we do. And it's B in terms of X, but we really don't care. What I'm going to do is I'm going to write it down below. I'm going to write it just B, because that B of X might kind of mess us up. We're just saying, again, that's giving us B, the number of bees. Now we got to plug in a value for K and then some daily high temperature to get that number of bees, but that's okay. So B is equal to 50, and I'm going to do a rewrite on the fly. So I'm doing, instead of radical, I'm doing the quantity K plus 2x raised to the 1/2 power. So all I did is I rewrote that function I just wrote a b is equal to 50 times the quantity k plus 2x to the 1/2. Now to magically make dB dt appear, what do I have to do? That's right, I got to take the derivative with respect to time. Okay, I got the left side, dB dt. Yay! Okay. Okay, right side's not too tough. It's really just chain rule. And don't forget k is a constant. So I'm going to go exponent times my 50, that'd be 25, plus k plus 2x, times the derivative of the inside function. Well, the derivative of k is going to be 0, but d dt of 2x is going to be 2 dx dt. Okay, I'm just going to write that. I'm doing d dt of 2x, and my answer to that is 2. And the derivative of my inside function x is dx dt. So that's how I'm getting this piece right here. Okay. Well, I'm liking that. I've got, actually, I do have a value here for dx dt, so I'm feeling good about that. What I don't like, though, is I don't have a value for k or for 2 or for x. Well, here's where this problem is, I think, extra challenging. If I go back to my original equation here, and I got b is equal to 50 times the square root of k plus 2x. And if I know I'm interested in dB dt when b is equal to 100, so I substitute in 100. And then I divide both sides by 50. I get 100 divided by 50 is 2 is equal to square root k plus 2x. Oh, I hope you caught this before I did. When I did the power rule right here, don't forget, I got to write raised to the negative 1/2 power. Okay, and I apologize for that. That would have been costly. If I rewrite this, just change it around a little bit. 25 times 2 is 50. And then I can write this part, that's negative 1/2. So I could write that as square root. I'm putting it down in the denominator because it's negative. K plus 2x, you might see where I'm going now. And then times dx dt. Okay, that, I know dx dt is given as 2. I got my 50. And looky-loo, look right next door here. We just worked this out. We know that 2 is equal to the square root of k plus 2x. Hey, that's what I got right here. So I just need to write that as 2. So 50 over 2 times 2 is equal to dB dt. I can stop right there. It's going to be 50. I can't help but simplify that. And so that is going to be the rate that the number of bees is changing with respect to time when 100 bees are spotted. So that is my answer right there. They didn't ask for units on this, so I'm not going to even mess with units. I'm just going to leave it just like that. Okay? Okay. That finishes off problem number 1. That was salty, but I know you guys can handle it. Okay. Question 2. So I've got, I need to find g at 8, and I need to find g prime at 8. Okay, so I'm given a piecewise function. It's defined on the closed interval from -4 to 9, graph of f. So this is f that I'm looking at. This is the graph of f. That's important to know. It's a semicircle, a quarter circle, and 3 linear segments as shown in the figure above. Let g be the function defined by g at x is equal to 3x plus the definite integral 2 to x f of t dt. So I know I'm going to have probably FTC part 2 floating around here somewhere. So part A is find g at 8. Okay. So g at 8, all I'm doing is I'm using my definition of g at x. G at 8 is equal to 3 times 8. plus the definite integral from 2 to 8 f of t dt. Well, that's equal to, I don't want to hurt myself, so I'm just going to do 3 times 8 again. Pretty sure that's 24, but I'm not sure. Plus, now this part I'm going to have to look at my graph. Okay, so I'm going from 2 to 8. So really I'm interested in from 2 to 8. And so I'm really going to be interested in that quarter circle. I'm going to treat this like a trapezoid. And then I got one more, I got a triangle. So I just have to come up with those 3 areas, and then also be aware of, is my function above the x-axis or below the x-axis? Okay, so my first one, that quarter circle, well, it's a quarter circle. So I know it's 1/4 pi, and my radius is 1, right? My radius is 1. So that'd be just 1 squared. So that's just pi over 4. My function's above the x-axis, so I'm going to treat that as a positive pi over 4. Okay, the next one, that trapezoid. Okay, the trapezoid, that's hard to see. Trapezoid is going to be, I'm looking at it this way, that the height is going to be 1 unit, and then I got a base that's 2 units, and it looks like another base that's going to be 1, 2.5. So that's 1 times 2 plus 2.5, average of those, that's what I've got. So that, leave it like that. I could also just call that, how about 4.5 over 2? And again, that's above my x-axis, my function is. So that was 4.5 over 2. Okay. And then the last shape, that triangle, it's going to be, triangle is 1/2 the base. My base, got to be careful here, is 1, 2, 2.5 by 1, 2, 3. 3 units. So I could call that 7.5 over 2. Now again, this one I got to be careful, that's below. So I'm going to do that minus 7.5 over 2. Okay. Okay, so that's G at 8. G prime at 8. Well, first thing I got to find is G prime at x. FTC part 2, G prime at x is going to be 3 plus, I'm just taking that x, putting it into my integrand, 3 plus f of x. So G prime at 8 is equal to 3 plus f at 8. Got to go one more step. Can't leave that because the function notation is going to be 3 plus f of 8. F of 8 looks like it's 0. So I'm good. So there's G prime at 8. Okay, part B, find the value of x in the closed interval from -4 to 9 at which G attains its maximum value. Maximum value. As soon as I see the word max, I'm thinking Table City. So I'm going, this is part B, and my table, so I'm going to put, I got x on the left column and G on the right column. So x, G at x, and then I'm looking at, I got to put in my endpoints, so -4 and 9. And then those are endpoints. Then do I have any critical numbers? Critical numbers are going to be where G prime is equal to 0 or is undefined. Hey, there's G prime right above it. So I'm going to set that. So G prime at x equals 0 is equal to 3 plus f of x. So really, I'm looking for, if I subtract 3 from both sides, I'm looking where f of x is equal to negative 3. So I'm looking at my graph of f of x. Negative 3 is right here. That's negative 3. Ooh, it's negative 3 at an x value of negative 1. So I'm going to add that to my table. And it's also negative 3 right here at an x value of 7. So it looks like I got to look at 4 values, 4 x values. So I'm going to plug those into g at x. And that's what I'm using for g at x is, I'm just going to write that. 3x plus the definite integral from 2 to x f of t dt. Okay, I haven't found any one of those values, so I'm going to have to go from scratch. So g at negative 4 is going to be 3 times negative 4 plus the definite integral from 2 to negative 4 f of t dt. So that's going to be equal to negative 12. And then I got to look at this. Now I notice that my upper bound is going to be less than my lower bound. So I'm going to be integrating from right to left instead of left to right. So that's from 2 to negative 4. Oh, sweet. Okay, that's just going to be what? It's going to be there's 2, and there's negative 4. So it's just going to be the area of that circle. Now, it would normally be, if I was integrating left to right, that would be negative, but because I'm going from right to left, I'm going to treat it as a positive value. So I just got to figure out the radius of that. Looks like it's 1, 2, 3 units. So it's 1/2 pi times 3 squared. So that's going to be 9/2 pi. So that is, and again, I want to treat that as a positive value. So that's going to be negative 12 plus 9/2 pi. Okay, that's my value for negative 4. So that's negative 12 plus 9/2 pi. Okay, next one is going to be, let's do at 9. So that's going to be 3 times 9 plus a definite integral from 2 to 9 f of t dt is equal to 27 plus, and now from 2 to 9. Okay, I went from 2 to 8. I got that one earlier, and now to do 9, I basically just got to go for this last rectangle right there. So I'm sorry, triangle rather. That's just going to be 1/2. The base is 1 unit, and the height is 1, 2, 3 units. So that would be 3/2. So what I had here for g at 8, I basically just have to take that, what I've got right there, and then I just need to add 3/2 to that. So that is going to be 24 plus pi over 4 plus 4.5 over 2 minus 7.5 over 2 plus that last piece I just came up with, 3/2. Okay. G at negative 1. Do that one down here, kind of running into myself here. So that's going to be 3 is negative 1 plus the definite integral from 2 to negative 1. Again, I'm going the other direction. It's going to be f at t dt. So that's going to be negative 3 plus, now I'm looking from 2 to negative 1. Okay, that's going to be right here. So I'm looking from 2 to negative 1. So I'm looking at just half of that. Well, I know that whole thing was 9/2 pi. So half of that is going to be 9/4 pi. And again, I want to treat that as positive because I'm integrating below, the function's below the x-axis, but I'm integrating from right to left. So it's 9/4 pi. So negative 3 plus 9/4 pi. So that is negative 3 plus 9/4 pi. Sorry, this is a hot mess. And last but not least, g at 7. So I'm 3 times 7 plus the definite integral from 2 to 7 f of t dt is equal to 21. Okay, now here, 2 to 7, I did g at 8. So let me see if this, yeah, what I can do is I can run with what I had here, and I just have to carve this triangle. Not really, because it's not exactly just cutting it in half. So I better just do that one from the get-go. So I'm going this piece, that piece, and then this triangle right there. Okay, so that's going to be that piece. And again, this is, I'm going from left to right, so I can just take it the way it is. So it's 21 plus, I'm just going to continue it over here, plus the quarter circle, which is pi over 4, plus the trapezoid, which was my 4.5 over 2. And then this orange triangle is 1/2 the base, and the base here is 1.5. So I'm going to call that 3/2 times the height, which is 3. So that's going to be 9/4. Now that's negative, so I have to subtract that. So that's minus 9/4. Wow. Okay, that was a lot of fun. What I'm looking for, I've got all those values. Now I want to find the x value in the interval where g has a max. Well, this max, it doesn't take too long to kind of look at it. This 24, and then this has kind of everything that this one has. And then this, but even with this, I'm going to say that, hey, my max is right there. That would be my max value. But again, what am I interested in? I'm looking at the x value. So I'm going to say that g at x attains a max in the interval from -4 to 9 at x equal 9. Okay? The good news is that justification is what I have for my table. Okay, part C, find the limit of f of x, f prime of x, as x approaches 2, or state that does not exist, justify your answer. Okay, here's the good news. If I clean this off, okay, if I lose that, and I'm looking at the derivative as x approaches 2, so here's 2. I'm looking at the derivative, so I should be thinking about what are the tangent lines doing as I am approaching 2. So the way I should answer this is the limit f prime of x, x approaches 2. What I have to check is the limit of f prime of x as x approaches 2 from the left, and the limit of f prime of x as x approaches to from the right. Well, if you can see, since those are my semicircle, my quarter circle, right here at this point, I'm going to have a vertical tangent. So I'm going to have the slope of my tangent line is undefined as I approach from the left, and it's undefined as I approach from the right. Well, now, because those are both positive infinity, that does not mean that my left and my right hand limits are equal. That's going to mean that the limit of f prime of x as x approaches 2 does not exist. Okay. Okay, the last one, D. Just copy that down. Okay, the limit of that expression as x approaches 3. I don't know about you, but I'm smelling L'Hopital on this one. If I just check it, what I got to show is I got to take it, plug it in the top. I want to separate it. I don't want to combine it as just one. So I want to do that. 8g at 2x minus 2 pi minus 160. And then I want to look at the limit as x approaches 3 of the denominator. E to the x minus 3 minus 1. Let's look at that as we plug that in. That's going to be e to the 0, that's 1, minus 1, that's equal to 0. Okay, the denominator is equal to 0. This one we got to work a little bit harder at. It's going to be 8 times g at 6 minus 2 pi minus 160. Okay, well, g at 6, man, they are making us work. I don't think we've calculated that. G at 6, there's 6. So that would cancel out. That would cancel out. And that would be g at 6. I'm just going to put that. G at 6 is equal to 3 times 6 plus my definite integral from 2 to 6 f of t dt. So I know that's 18 from 2 to 6. Well, that's my quarter circle. That was pi over 4. And then since these are canceling out, that's just going to be 2 units right there. So it's plus 2. So that's going to be 18 plus pi over 4 plus 2. So that's g at 6. So that is 8 times that hot mess right there. 18 plus pi over 4 plus 2. 18 plus pi over 4 plus 2 minus 2 pi minus 160. Well, you can kind of see if I take the 18 and the 2 and I make that 20, 8 times 20, okay, there's the 160, which is going to cancel with that. And then if I do 8 times pi over 4, that's going to be 8 pi over 4, which is the same as 2 pi. And then I'm subtracting 2 pi. So wow, that was a lot of work, but that means my numerator also works out to be 0. So it is going to be L'Hopital. So it's L'Hopital. I'm basically going to take the derivative of the numerator and the derivative of the denominator. So if I'm looking at d dx of the numerator, actually, I'll just kind of walk through it. So it's going to be 8 times g prime at 2x times 2. Okay, and then all the rest of this is going to go away. That's because those are constants, kind of like that. Over, and then the derivative of the denominator is going to be e to the x minus 3, and that's it. And now again, I'm looking at the limit as x approaches 3. And so here, I'm feeling pretty good about this because it's going to give me e to the 3 minus 3. Well, that's going to be 1. It's e to the 0, which is 1. Okay, so I know I don't need to do L'Hopital. Again, I'm either going to get the limit does not exist or I'm going to get a value here. So this is going to be 8 times g prime at 2 times 3 times 2. So that's going to be g prime. So I need g prime at 6. Okay, well, g prime, okay, there it is, g prime at x. So g prime at 6 is equal to 3 plus f at 6. Okay, so f at 6 is equal to, f at 6 is equal to negative 1. So I got 3 plus negative 1. G prime at 6 is equal to 2. So I get 8 times 2 times 2. So that is going to be my answer, 32. And that was dangerous to simplify that numerically. All right. All right, guys. Hope that helps. Those were a couple good salty problems. Again, thanks to Michelle Crummell for putting that problem together for us. All right, guys. Send me an email if you have any questions.